So does everybody understand that these two forces that I'm showing are components that together make up the frictional force that could be anywhere in this plane? Herman, you don't like that.
Yeah,
There's just no other forces that
I understand the F problem. I just don't see the F.
Okay, let's go back to this surface right here. We know that parallel to this surface, there can be a frictional force, but we don't know if it's this way, or this way, or this way in the surface. It could be in that plane, it could be rotated 360 degrees. That's what I'm saying.
I would break with that. There's no other forces in the E tangential direction.
Okay, don't go there. When you draw the free body diagram, I want you to account for any possible force there is.
Oh, okay.
Don't, like I always say, that's future tripping. You know, you don't assume that that's going to be zero. It actually is zero in this problem because you're absolutely right. There are no forces in that direction. But I want you to, I at least just want you to account for the possibility that it could be there. And I want you to see that what I've done is I've taken this surface and realizing that there can be a frictional force in any direction of this surface. And so what I've broken it's just like, you know, the XY plane. It's like, okay, I'm just going to say, I don't know what the vector P is, but I'll break it up into components Px and Py. It's the same exact idea. I don't really know where that vector is in this plane, but I've broken it up into that direction and that direction. This direction is this force here, frictional force here. This direction is the tangential direction. Yes.
Question, is the friction force is only tangent to the path?
Tangent to the what?
To the path. If
That's
it's going
right. And
way,
this
it's
path,
going up.
no, not the path, the surface. The surface, okay? That's the difference.
Yeah. So it's because the motion, if the slide is going down, it should be going up.
Right, and that's why I showed it this way.
Yeah. So well, yeah.
And this one,
Yeah,
you know, Herman's right. There is actually no force that's even trying to move it in the tangential direction, and so, you know, so it was hard to pick a direction, so I just showed it like that. But all right, so this is the hardest part of the problem. If you buy into this free body diagram, then we can just go ahead and draw the inertia vector diagram by just showing the acceleration vector in the components of the normal, tangential, and binormal directions. So MAN, MAT, and then MAB, and we know that this is always zero, right? It is. The acceleration in the binormal direction is always zero.
Oh, yeah.
So why did I show it? I don't know, just because I like to have completeness and show it's a three-dimensional problem. There really should be three components of the vector, and so I'm showing all three components, but we know by the definition of normal and tangential components, just the way they're defined, AB always has to be zero. So I drew it there just because I like to see three vectors, but okay. So now, you know, I actually feel like I'm almost done with this problem. And you should realize that a lot of times it doesn't take a lot of writing to get most of the credit for a problem. And so I want you to be very judicious in what you put on your paper. Don't just treat it like the kitchen sink. You know that expression, just throwing everything in and the kitchen sink. And think, oh, I'm sure I'll put something there that will be worth getting credit. If I have to dig down and look for something to give you credit on, I'm going to be so irritated by the time I find it, I'm not going to give you any credit. I'll probably give you a little credit, but I might take points off if you put stuff that's ridiculous. Okay, so don't approach these problems like that. Just really know what you're doing and put meaningful things on the paper. So here's my free body diagram. It's equal to my inertia vector diagram. And really, the rest of the problem, the math gets pretty hairy, and I don't really want to do the math, and I'm not going to do it for you. I don't even want you to waste your time on the test doing the math. I just want you to get to the point where you feel like you've solved the problem and that the only thing that's left is the math part. So let me show you what I mean by that.
So if we have like 3 equations, 3 unknowns,
Yeah, exactly.
just set it up.
Exactly. 3 equations, 3 unknowns, you're done.
Should have said that in the last test. Oh, that wastes so much time.
Okay, so, sorry about that.
So now the component of F is,
So really now it's just like a statics problem. You just break it up into each direction, but you know, it's not static, so it's not 0 acceleration, but it looks like that. And then we're going to have, and actually the two, you know, this one actually isn't going to give us much because
because they only have FT.
yeah, okay, so this is just the general equation. The sum of all the forces in the tangential direction is equal to the mass times the acceleration in the tangential direction. Ft, okay, so we know that this is 0. Why do we know that's 0?
Because the speed is.
Yeah, because it says that it's rotating with a constant omega. So that means that the acceleration in the tangential direction is 0. So now we know that the force in the tangential direction is 0. But you know, actually, Herman, going back to what you were saying, if they had told us that omega in this instant was 14 radians per second, but they didn't tell us that it was constant, then Ft actually wouldn't have been 0.
You're right.
So I'm sure glad that I have it on my picture. But of course, in this case, it is 0. Okay, so I want to see first your general equation and then the specific plugins for this problem. Okay, so again, it's just, you know, like statics, and you just plug in to each component of F equals ma. So we did it for the tangential direction. For the normal direction, okay, the geometry gets a little bit hairy. Let me carry this angle. Okay, so this angle here is theta. We need that angle to do this equation. So in the normal direction, okay, let's see. We got this perpendicular to this. This. Okay, so this is theta right here. So it's F cosine theta. Okay, so that's the component of the frictional force in the normal direction, times N sine theta is equal to MAN. What's AN?
V squared over.
Yeah, it's V squared over R.
So omega squared.
And do I need to show you why that's equal to?
You can say omega squared R.
Yeah.
Okay, good. So that's MR omega squared. Everybody's fine with that? Okay, great. Okay, so there's an equation with our unknowns F and N. So theta is not really an unknown because we're going to plug in specific values of theta. Okay, so this is equation 2, and then in the binormal direction, let's see, we've got mg minus n cosine theta plus f sine theta.
It's minus F.
Well, the binormal direction is down.
Yeah,
So mg minus n, oh, yes, thank you. Thank you. All right.
So it's solved.
So why do I, wait a second, why do I have it different on my paper?
You probably just, if you took the different direction, if your F is down, you're probably gonna have plus. We don't know that anyway, so it's still whatever.
No.
Because F is going up.
Oh, you know something? I have
The
n.
block is
That's
side.
interesting. On my, I know why there's a difference, because on my paper, I have n going this way. So that goes back to your question, you know, why didn't I account for the forces up here? And I said, oh, because I just didn't feel like it. But even if I had, I said that they would just be combined with this n, and it would mean that n isn't necessarily in this direction. And in fact, in my solution, I do show n the other way.
Yeah, I'm still confused on the slide. So now the forces, is it the reaction is from top or from the bottom? So when
Well, we don't know. Let's not make any assumptions. So I'm just saying, well, in this picture I have n going this way, and so I'm saying if I get a positive value for n, then this is the correct direction. But I actually don't know at the outset. Because it could be that the forces from the top are acting down on it. I kind of don't think so, but it doesn't matter. You know, I don't have to know at the beginning of the problem. All right, so now that we've got these two equations in two unknowns, I feel like I'm done.
Yeah.
Do you all agree? Okay, so let me, but I would want you to like say something about it. You could say something about,
You can
I can solve for f and n from these two equations, and then check to make sure, so solve for f and n, then check. What do we want to make, what are we checking?
check if it's sliding or not.
So we want to make sure that f, the ratio of f to n is less than, well, less than us, which was given as 0.35. So if it is,
Not sliding.
then it's not sliding. Okay, so at least like I know you know how to finish it, even if you didn't want to bother doing the math. Okay, so let's go on to the next problem. Cut.